Let me begin my introduction to group theory by telling you about my first encounter with group theory. There is a famous problem in computer science called the graph isomorphism problem. Given two graphs, decide whether one can be transformed into the other. For example, these two here might look different on first glance, but watch how they are just reshaped versions of one another. How about these two? Probably not the same, since one has a crossing while the other one doesn't. Well, turns out they are the same, despite the crossing. So here's an example where they have to be different simply because one has 5 nodes while the other one has only 2. But most problem settings are not that easy. Try to see if you can solve this one. There is a straightforward algorithm to decide whether two graphs are the same. Just brute force all possible node positions. If one possibility works, good, but if none of them work, they truly have to be different. But there are exponentially many possibilities, so this takes a lot of time. We would prefer a faster and cleverer algorithm, preferably one that has a sub-exponential runtime. Research into this problem took off in the 80s, but it took roughly 4 decades until Professor Laszlo Babaj found the first such algorithm in 2015. His result was a massive achievement, so when I saw that Babaj gave a talk explaining his algorithm, naturally I wanted to check it out. But before he even started with his explanation, already in the introduction, he came with
So, group theory introduced into the subject.
Group theory? Really? I didn't know any group theory. I'm a mere computer scientist, not a mathematician. But even though I only uploaded 3 videos so far, you guys already know that I would do anything for a nice algorithm, even if this means that I'd have to learn group theory. So that's what I did. And my god, you cannot imagine what techniques the mathematicians have kept secret from us all this time. There is this whole field called abstract algebra that basically no one has ever heard of, but is absolutely essential in higher math. You have to understand, we all started school learning to count using the natural numbers. Later we learned that there are also negative numbers, so we get introduced to the integers. Then we run into the problem that we can't exactly divide 3 by 2, so we encounter fractions. And finally we learn that there exist irrational numbers like the square root of 2, which cannot be described as a fraction. So in the end, they tell you that the so-called real numbers are the ultimate number system and that you can find every number you'll ever need in your life somewhere on the real number line. And that's where the school curriculum ends for most of us. But you might have heard that in the 16th century, some Italians started to use the square root of -1, something that cannot be found on the number line, but that lives somewhere outside it. They had their reasons for doing so, which we're not going into. But the point is that they slowly realized that with this, they invented a new number system that they thought was useless in real life and yet works better than anything they'd ever seen before. With time, mathematicians tore down more and more of the tradition that the real numbers are the ultimate system, and they started inventing new number systems left and right. Some number systems you probably never even knew existed, like the Hamiltonians, finite fields, and the p-adics. The mathematical landscape exploded in variety, and with so many number systems out there, mathematicians searched for an abstract, unifying theory. A set of rules that governs all these systems and that captures their behavior. But what kind of rules would make sense? How do we know that our theory accurately describes all these number systems? This is a very tough question to answer. Mathematicians tried several different sets of rules, always retrying and refining. And while the names for these abstractions certainly could have needed some improvements, after decades of work, certain rules started to crystallize, certain rules that they could agree simply make the most sense. One particularly simple but nonetheless powerful theory that started to manifest is the theory of groups. Groups are powerful enough to describe the most various things. They were originally invented for the very specific purpose of analyzing permutations of roots of a polynomial, but were later used for more common problems such as number theory, geometry, physics, and making young men go nuts. In fact, 4 out of the 7 Millennium Prize problems, you know, those problems where you win $1 million for solving any of them, use groups in their definition. But despite their sheer power, groups are so easy to get into that I decided to make a series on them, starting with this video. So, what is a group? A group is a collection of elements, can be whatever, numbers or any other mathematical objects you desire, together with one operation. Again, can be whatever, addition, multiplication or something completely different. They just have to satisfy these 4 axioms. Let's go through them. The first one is called closure. It says that the operation takes any two group elements and gives you another element of the group. That's it. Seems pretty anticlimactic, but I mean, calculating two things together is something we do all the time, so at least this shows how groups are supposed to be an abstract generalization of, you know, most math things. But the important part is that the math thing the group describes is a closed system, hence the name closure, in the sense that since the result is again part of the group, you can continue to operate group elements onto it, which brings me to the next axiom. The associativity we all know from addition and multiplication. Formally, it says that when operating three elements together, whether you first operate A and B, or first operate B and C, the result in the end is the same. In practice, this means that we can just write everything without parentheses, because there's no ambiguity about the order in which you calculate. The next two rules are a bit more interesting though. The third rule says that every group contains a so-called neutral element, an element commonly denoted by E that, when operated with any other element, leaves it be, no matter from which side this happens. So it's like an abstract generalization of adding a zero. Just a remark for the English-speaking people. For you, it's more common to call it the identity element, and it's the French, the Germans, the Italians, and pretty much anyone else that calls it the neutral element. In my humble opinion, neutral makes more sense, especially if you're new to group theory, so that's what we're going to roll with from now on. And the final rule says that every element has a corresponding so-called inverse element, always denoted with a -1 in the exponent. The inverse element, when operated on the original, annihilates both elements and returns the neutral element. Let me justify the name inverse. Let's say we start with A and operate B and C and D onto it. If you now want to revert all those operations, you just apply the respective inverses. First, the inverse of D gives, with D itself, the neutral element, and the neutral element vanishes anyway. Likewise, we can apply the inverse of C, which with C gives again the neutral element, which vanishes too. And now the inverse of B, you already know that they cancel. I'm not even gonna bother to animate the whole ordeal. But look, we're back at A. So the inverses, as their name suggests, reverted all previous operations. Also, the notation for the inverse has a sensible purpose. In group theory, it is legal and even very common to abbreviate A operated on A operated on A operated on A simply as A to the 4, as you know it from multiplication. When you now operate the inverse of A to A to the 4, think about what happens behind the scenes. The inverse cancels one of the A's and we're left with 3 A's. So essentially A to the -1 subtracted 1 from the exponent, which is pretty much what the notation indicates it would do. But yeah, any mathematical structure that satisfies these 4 axioms gets the privilege of being a group. You're probably curious by now what such a group could look like, so it's time for some examples. The integers, denoted with a z, with addition as the operation, form a group. Indeed, closure is satisfied as you can always add any 2 integers and get another integer. And we all know that addition is associative, which again means that order doesn't matter, and that is reflected in the fact that we usually don't write down parentheses. Already in the definition of groups, I've hinted that 0 is the neutral element, as indeed 0 added to any number is that same number, no matter if it's added from the right or the left. And for the last rule to hold, we just need to show that every integer has an inverse, which added together returns the neutral element. That would be its negative, so all conditions are met. Very well. On the other hand, the integers with multiplication as the operation do not form a group. I mean, let's check the axioms. Closure is satisfied because multiplying 2 integers gives another integer. Associativity is also satisfied. The neutral element is now 1, as multiplying by 1 leaves any element b. But it's the last rule that is not satisfied. For it to be satisfied, we would need to be able to get from any element back to 1. But to get, let's say, from 4 to 1, we would need to multiply by a quarter, which is not an integer and doesn't exist in this domain. So not all rules are satisfied, and this system does not get the privilege of being a group. But this hints that the rationals under multiplication do form a group. If we allow not only whole numbers but also rational numbers, which are denoted by a q, then the first 3 rules hold as discussed, but now for any number, the inverse is its reciprocal. Except there's one hipster that has no reciprocal. So it is customary to exclude 0, which makes it so that all axioms are indeed satisfied, and we therefore have another example for a group. We have a problem though, because if you check the 4 axioms, you'll realize that the rationals also form a group under addition. To differentiate between these two groups, one adds the respective operation symbol to each group, and it's expected from good group theorists to know that the group where we multiply is all the rationals except 0. All 3 groups we've looked at so far have infinitely many elements. How many elements a group has is called the order of the group, and is written with these 2 bars. But in the early days of group theory, groups commonly only had finitely many elements. So let's look at some finite examples. The cyclic group, denoted by the n, is actually a whole family of groups, because the n denotes just a placeholder for any positive integer of your choice. Here, I'll choose 6. Then C6 behaves pretty much as the ordinary integers would do, in the sense that we start at 0 and repeatedly adding 1 gives 1, 2, 3, 4, 5, but when we get to 6, we wrap around and start again at 0. This cycling back around is where the name cyclic comes from. So in this group, 3 plus 3 does not equal 6, but it cycles back to 0. Similarly, 4 plus 5 would usually give 9, but since we cycle back at 6, 7 equals 1, 8 equals 2, and finally 9 actually equals 3. Apart from the fact that the cyclic group has finite order, Z6 has 6 elements and Zn has n elements, not much has changed compared to the integers. The system is still closed, addition is associative, and adding 0 doesn't affect the result. It's just that now the inverse of, let's say, 1 is not minus 1, since that doesn't exist, but 5. And the inverse of 2 is 4. For 3 it's 3, for 4 it's 2, for 5 it's 1, and for 0 it's 0 itself. Apart from 0, in general in Zn, the inverse of a number a is n minus a. In all 4 groups we've looked at so far, the elements commute, meaning that a operated on b is the same as b operated on a. But be careful, even though the circle looks and feels like a multiplication symbol, it is not. There is no rule that says that they should commute. So I want to introduce one final example in which the elements do not commute. The dihedral group, or short dn, works as follows. Choose any regular polygon. Here I'm going to choose the hexagon. The dihedral group, since I've chosen a 6-sided polygon written here as d6, is the different ways to transform space such that the hexagon stays in place. There are 6 rotations that do exactly that. 0 degrees, 60 degrees, 120 degrees, 180, 240, and 300 degrees. A full 360 rotation transforms space in the same way that a 0-degree rotation would, so it's not counted as a new element. But we can also flip the hexagon. And combining the flip with the rotations gives us 6 more elements. And if you think about it, the hexagon only has 12 possible configurations it can be in, so these 12 elements are already all the transformations. By the same reasoning, we see that the order of dn, the group of transformations for an n-sided polygon, is 2 times n. Again, n rotations and n flipped rotations. The operation of this group is the chaining of these transformations. For example, chaining a 60 degree with a 240 degree rotation gives you a 300 degree rotation. And, you know, we could verify that this makes a group. Anyway, what I'm going to demonstrate here is that the order of elements does matter. For a given hexagon, if we flip it and then rotate it by 60 degrees, we get this transformation. But if we rotate it first and then flip it, then we get a different transformation. In general, a flip and a rotation is not the same as a rotation and a flip. The former obviously gives a flipped rotation, and the latter turns out here equals a flipped 300 degree rotation. So now we've seen 5 examples of groups, but the power of group theory does not come to fruition by looking at groups one by one individually. The whole point is that when you prove theorems for the abstract concept of a group, they automatically hold for all instances of groups. So it's time we prove theorems the way it's done in group theory. First of all, I would like to justify the name of the neutral element. I talk about the neutral element as if there was a unique one, but couldn't it be that a group contains several neutral elements? It turns out that this is not so. Suppose that there were the neutral elements E1 and E2. What would happen if we operated them together? On one hand, since E2 is a neutral element, this equals E1. On the other hand, since E1 is a neutral element, this also equals E2 at the same time. This is only possible if E1 equals E2. By the laws of mathematics, if two things equal each other, they are the same thing. So instead of two separate neutral elements, a group always has only one. Let's prove another theorem similarly. By definition, every element has an inverse. But that means that also the inverse has an inverse. Let's again just operate all these elements together and see what happens. On one hand, A and the inverse of A cancel, so this equals the inverse of the inverse. On the other hand, the inverse and its inverse cancel, leaving A. So this means that the inverse of the inverse is just the original. This is just like how the negative of -3 is just 3, except abstract. But do you realize what this means? Have you wondered why the neutral element has to be neutral from both sides, but the inverse only needs to invert from the right? It turns out that we don't need to assume left-sided cancellation as an axiom, because not only can we prove that, but we just did that if you think about it. The group axioms only allow us to cancel inverses from the right. But A is an inverse, namely the inverse of the inverse, so this is perfectly legal. Now that I say it, maybe I should also justify the name of the inverse. I talk about the inverse element as if there was a unique one, but couldn't it be that an element has several inverses? Again, there's not. Let's assume there were a second inverse, and let me operate it from the left to both sides of the definition of the inverse. How fortunate that we've just proven that inverses also cancel from the left, so we can simplify. Again, by the laws of mathematics, we see that the second inverse is just the original inverse, so inverses are always unique. This fact is really convenient because it allows us to upgrade our notation. What is this object? We know that inverses are written with a -1 in the exponent and squares are written with a 2 in the exponent. But this? There are two possibilities that come to mind. It could be the square of the inverse, or it could be the inverse of the square. Well, it turns out that those two ideas are actually the same. Both objects invert a squared. I mean, per definition, the inverse of a squared inverts a squared. But watch, so does twice the inverse. Since we've just shown that there can be only one inverse, there's no difference between them, and it is customary to write that object as a to the -2. This is just like how there's no difference between 3 plus 3 negated and 3 negated plus 3 negated. Both objects are denoted by -6. The same reasoning extends to any negative power, but let's stop here. I've already proven 5 theorems in such a short time. Again, the uniqueness of the neutral element, that the inverse of the inverse is the original, that inverses also cancel from the left, the uniqueness of inverses, and finally, the inverse of the square is the square of the inverse. But if you too want to have a try at proving such theorems, I can give you this challenge. The group axioms I have given you are not the weakest ones. You can actually remove left-sided neutrality, and yet the definition of groups is unchanged in the sense that we can prove left-sided neutrality as a theorem. So go ahead and try to do exactly that. I didn't want to work with these weaker axioms here, since that would just double the length of our proofs without gaining that much more insight. We're at a point where I feel like I need to justify myself. These theorems are supposed to uncover the hidden structure of mathematics, but when I talk about how the fact that negating the negation and taking the reciprocal off the reciprocal both give back the original is just an instance of this underlying theorem on inverses of inverses, it just makes me feel like a nutjob rambling about how all number systems are secretly ruled through group theory. But what's the point of proving abstract theorems if we never get something concrete out of it? It's time we study the big picture in group theory to see where this is all going, and prove our first big theorem along the way. And what better way is there to study groups than with more groups? A subgroup is just part of the group that also happens to be a group itself. For example, the even integers are a subgroup of the integers. Even though they are just a subset of the integers, they still satisfy all 4 axioms. Let's for example check the last one. The inverse axiom is satisfied since every number indeed has an inverse. On the other hand, the odd integers do not form a group because they don't even satisfy the very first rule, the closure axiom. An odd integer added to an odd integer gives an even integer, which is outside the domain of odd integers, so they do not form a closed system. As another example, D6 also has subgroups. For example, it's intuitively clear that the rotations do form a closed system, since a rotation and a rotation gives you another rotation, and proving that they indeed are a subgroup is just routine. D3, the symmetries of a triangle, is also a subgroup of D6. But if you think about it, that makes sense, as any transformation that is valid for the triangle is also valid for the hexagon. And as a final example, in Z9 there's the subgroup of 0, 3, 6. I again don't want to prove now that this is a subgroup, because I think it's again intuitively clear that this is at least a closed system. All elements are multiples of 3, and if the only thing you can do is move around with multiples of 3, you're obviously going to be locked into this system. There's nothing really much else to say about subgroups. I could bombard you with 10 more examples of subgroups, but I think they're very intuitive. So instead, I'd rather explore why our intuition works so well, why locking yourself into a closed system gives you a subgroup. Just how the subgroup of rotations can be expressed as multiples of the 60-degree rotation, and the 0, 3, 6 subgroup can be expressed as multiples of 3, in general, for any element A, the so-called subgroup generated by A is defined as the multiples of A, which are just A squared, A cubed, and so on. This system is obviously closed, since operating a power of A with another power of A gives you, again, a power of A. I claim though that for finite groups this is indeed a subgroup, even though it looks like the neutral element and inverses are missing. But let's look at what happens in a finite group when we keep on generating powers of A. At some point we simply run out of elements, and sooner or later we have no choice but to generate the neutral element as a power of A. After that, this process runs into a cycle, since if A to the 8 returns to E, then A to the 9 is just A again, and so on. And it's not hard to see that we now get inverses for free. If A to the 8 equals E, the inverse of A is just its own 7th power. Just one thing that I'd like to clarify is why the cycle has to return to the neutral element before repeating, because why couldn't A to the 8 go straight to A? Well, if A to the 8 equaled A, then cancelling an A from both sides, we see that already A to the 7 got to the neutral element. So in this sense you cannot avoid the neutral element, so the proof works out. Remember though that this works only for finite groups, because it can fail horribly for infinite groups. Trying to express the subgroup of even integers as a subgroup generated by 2 will generate only positive multiples of 2, completely missing 0 and the inverses. In such a case, to make this a subgroup, one makes life easy and includes the neutral and the inverse elements in the definition of the subgroup generated by A anyway. But again, only if needed. So to bring my point across, I have a second challenge for you. Find an element in an infinite group whose generated subgroup doesn't need the neutral element or inverses included. With our fancy new notation for subgroups, we have an opportunity to do a deeper understanding of groups. It turns out that groups are highly symmetric with respect to their subgroups, and what I mean by highly symmetric is that shifted copies of the subgroup appear all over the place inside a group. In the integers, for example, we have the even integers, but also the odd integers, and while we saw that the odd integers are not a group, they are at least a shifted copy of the even integers, where every element is shifted by +1. The mathematical term for such a shifted copy of a subgroup is a coset. Again, since it's not a group, we wouldn't call it a cogroup or something like that, but it is more than just any random set of elements, so at least it has a distinguished name. The coset is then denoted with that shift in front of the subgroup, so here the odd integers are 1 plus the even integers. Note that there is some ambiguity, because we might as well have gotten the odd integers with a shift of 3, so writing the coset as 3 plus the even integers is just as legal. Furthermore, since a shift of 2 or even a shift of 0 gives us the even integers themselves, a group does count as its own coset. We can also find such symmetries in D6. Here we have the rotations, which are a subgroup, and the flipped rotations, which are the rotations shifted by a flipped and are therefore a coset. You could shift the rotations by a rotation itself, and while that would shuffle the rotations around, the 0 degree to the 60 degree, the 60 degree to the 120 degree, and so on, the subgroup itself would be unaffected. So the dihedral group has this innate symmetry between normal hexagons and the flipped hexagons. But we can take it even further. Let's turn the game around, and instead of starting with the rotations and then shifting with the flip, we start with the flips and shift with the rotations. The subgroup generated by the flip generates just 2 elements. The flip, and flipping again, brings you back to the neutral element. Shifting that subgroup by 60 degrees gives the 60 degree rotation, and as I've noted before, a flipped 300 degree rotation. Shift by 120 degrees and we get another 2 element coset. And so on. By the way, we don't need to shift by flips, since that would just again shuffle the elements in the coset around, but not affect the coset itself. In the end, we uncover a new 6-fold symmetry in the dihedral group. This diagram gives us a complete understanding of this 6-sided symmetry, and the 2-sided symmetry is also easy to grasp, but what I think is more important is what you're not seeing in these diagrams. Why is it that a group can always be organized so neatly? You know, it could have been that there are the rotations, the flipped rotations, and another weird third coset. But there isn't. Every element appears once and only once in these cosets in a neat and ordered way. Why is that? I promised you that groups are highly symmetric with respect to their subgroups, and here we have a way to quantify that. Let's say we have a group with a subgroup inside it. I want to show that the coset of the subgroups neatly partition the group into equally sized fragments. There are two facts that are easy to grasp. The first one is that the cosets cover the whole group, because if you want to cover any specific element, you do what I think is the most obvious idea. Shift by exactly that element. Notice how then the neutral element shifted by x gives exactly x, covering it along with the other elements in the coset. The other fact is that all cosets are of equal size. Obviously, you don't suddenly get more elements by shifting, but you also don't get less elements. At first, it doesn't seem impossible that you'd lose elements, so to speak, by having two shifts converge to the same result. But for any shift, we can also shift back to the origin with the inverse element. Look, notice how the inverse cancels here from the left. I told you our proofs would come in handy at some point. So, if you can recover all original elements like this, a coset smaller than the original subgroup would now make the inverse shift suddenly give you more elements, which is also nonsense. No, it only makes sense for all cosets to have the same number of elements as the original subgroup, since each of the elements are in a one-to-one correspondence, by a shift in one direction and by the inverse shift in the other direction. The only fact left to discuss that is not at all obvious is that different cosets don't overlap. But let's see. Either you shift by an element that is already in the subgroup. Since the subgroup is a closed system, the results are all in the subgroup. Or you shift by an element that is outside the subgroup. Could it happen that any result is still in the subgroup, for example z times a equals b? Cancelling a from both sides and solving for z, we get that z equals b times the inverse of a. But since a is an element of the subgroup, so is the inverse of a. And since b is also an element of the subgroup, so is their product, again because of closure, so z must be 2. If we specifically assume that z is outside the subgroup, the result could have never been in the subgroup in the first place. So we have this dichotomy where a coset either doesn't overlap with the subgroup at all, or it is the whole subgroup itself. And basically, the same argument shows that this dichotomy also holds between cosets, but I won't repeat all the details here. All in all, this proves that the cosets partition the whole group into equally sized parts, and for finite groups we can summarize this with a really cool and very easy to remember theorem called Lagrange's theorem. Lagrange's theorem states that for a group G and a subgroup H, the order of H divides the order of G. And we've seen this, right? D6 has 12 elements and the subgroup of rotations has 6. Because we have now rigorously proven that the rotations partition D6, 6 has to divide 12. Or if we take a look at the cyclic group with 6 elements, it has subgroups of order 3, 2, and 1. And there cannot be subgroups of order 5 or 4. Fun fact about Lagrange's theorem: Lagrange died before group theory was even invented. Makes you wonder how he got his name attached to group theory theorem. It's complicated. And it's not like abstract algebra is known for good naming. Anyway, so what is this theorem useful for? Can you imagine the consequences this theorem has for a group with prime order P? Since primes can only be divided by 1 and P, a subgroup can only have 1 or P elements. Now, take any element that is not the neutral element, let's call it A, and start generating a subgroup. That subgroup contains more than one element, and therefore has to contain all P elements. So after we eventually reach the neutral element, we will have filled the whole group. This makes it eerily similar to the cyclic group. So here's a trick. Instead of the letter A, what if I use this symbol? And instead of this weird circle operation, what if I write plus? Then a squared becomes 1 plus 1, which we humans write as 2. And a cubed becomes 1 plus 1 plus 1, which we encode with this symbol. A to the 4 becomes 4, and so on. And for E, let me use the digit 0. So only through relabeling we got the cyclic group. But how I write down my group doesn't change anything about the group itself, right? Which means that any group of prime order, no matter how abstract, has to be the cyclic group. When I saw this, I felt like I understood group theory. Yeah, we could spend all of our time with abstract groups, but it is also possible with the sheer structure alone we get from the 4 axioms and a small size requirement to create very concrete examples. It made me want to go on a quest to uncover the hidden structure of groups of any order. I claim that with what you've learned in this video, you can guess, maybe even prove, what all the groups of order 6 are, and with the upcoming videos, we'll tackle the problem of uncovering all the groups. Wait a minute, weren't we originally trying to solve the graph isomorphism problem?